No, no, I don't. No, stop with the ads.
Mm, I'll try that. Okay. There you go.
All right. Which has the least delay, so I go with that.
Oh, my bad.
No, I got it. I got it.
Okay.
And then your profile thing on the right hand
Yep.
side sit a little
Yeah, I
bit, but
know. I was just working on that one. Yeah, so I got it to work on my Mac, so that was fun. Did that on some of the streams. It actually does both, which is kind of cool. It does like you can compile both Intel and ARM. It'll generate both of them. So, although
that's pretty wild, man.
the Intel one is just 64-bit, which is fine. It's it'll work.
It's the standard.
Yeah, it is. Although I have an old. I say old. I bought it in 2020. Of course I bought it. I've done this twice now. I've bought like the previous generation right before they released the new one. So,
It's just on the wrong cycle.
well, so in 2000, I want to say 6, I bought a iBook, and like within months, they're like, "Oh, we're switching to Intel." And I'm like, "Oh, great. I got a PowerPC one and you're switching to Intel."
And you had to use
So,
Rosetta and all that jazz to make things work after that.
yeah, well, Rosetta actually was I mean, Rosetta was pretty good, but that was for the when you bought an Intel one.
But
So
Intel and go back, yeah.
it took me a while. I think I got my next one then in 2009.
Yeah. I missed my old polycarbonate white MacBook. It was
Really?
like
I like the metal ones. I don't miss the
the polycarbonate one.
no, I do not. What I miss is the one that looks like a lamp. So it had the base, right? And it had a little arm that came up and then it had the
Oh yeah, yeah, yeah.
it looked like something from Pixar.
Yeah, that's exactly what I was thinking. Yeah. I had a 2016 that I really liked. It was like right before they went to the butterfly keyboard and the touch
Oh yeah.
bar.
Yeah.
That thing was a workhorse, man.
Oh yeah, that was great. And the fact that it didn't have the touch bar, like the keyboard is like Mac keyboards are fine. Like
I
their
like.
trackpads are the best. Like I dare anyone to show me a trackpad that's better than a Mac trackpad.
Oh yeah, it's not like I wish my Lenovo had the trackpad of the MacBook and the
I I
keyboard.
I, I have a Lenovo, I have a Razer, I've had Dells, I've had Linux. Like basically if it's not my Mac, I'm grabbing a Logitech mouse
Yeah,
and using
same
it. Cuz I and the Logitech mice are really good. They're comfortable. Apple mice, funny enough, Apple mice suck. Like they're just awful.
here. Yeah,
Like I had the like both of them
I had the
Logitech
little
mouse.
external touchpad at my
Oh,
last job. That because it had the same look, it's had the same feel as the
yeah.
one on the computer itself. Yeah, I like that one. Unfortunately, it stopped working.
Just well, it's Mac. It's It's a Mac. It's not. They don't care if it's supported. It's
Oh no,
okay.
it not that it wasn't supported anymore. It just physically stopped working.
Yeah.
And it was the new thin one. It didn't. So it was like, I'm not going to be able to get this apart without destroying it. So I'm not even try to fix it. So
Yeah. 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 I think. Well, like I took apart once a Surface or Surface Pro, and that was like using a heat gun to get the thing apart.
yeah, dude, that sort of thing
I
scares
don't
me.
think it went back together. I had a student help me with it, and it just it was never the same after that.
Yeah, that's the reason why I got my Lenovo. I can still take it apart.
Yeah. All right. So it looks like VS Code helped me here, or Copilot. So I think that should be a good size. I can. Okay. So, if we have just two numbers, right? So our first two arguments are going to be here in RSI and RDI. Um, is that okay for size
It
wise?
might need to be a little skosh bit bigger.
Okay. I don't actually need this one to be.
Oh, yeah, I can read it now. For one on the left, yeah.
Yeah. Okay. So, if we had a simple function where we just wanted to add the first two parameters together, we could do an, move RAX, RDI, add RAX. Right? And so like our return result is in RAX, right? One of the things we talked pre-stream is that data moves that way, right? So your data is always moving from,
Right to the left.
and if you think about it, like that's kind of how C works, right? So if you say X is equal to, X times X, or, C is equal to X times X, right? You're doing the result and you're moving the thing on the right side to the left side. So it is similar in that sense. Mathematicians, of course, will get drove crazy by the fact that you know it's not any actual equality, right? Because x cannot equal x times x, but that's just math
It's
people.
semantics.
Yeah, it's not possible. Um, so we can also look at, you know, let's say we wanted to add 8 things together. So we've got arguments 1 through 7. So let's do, and this one should work. So if we, do a move RDI, sure, the number 5, move RSI 6. So if I add those together, let me double check what I put in my, so we do have print int. Did I have a print hex? I don't think I did. Yeah, it's fine. Okay. So we can say call print int. And maybe even, I like to put a new line in there. New line.
Give it some space.
Yep. Ooh. Oh. And I need to, well, it should be in print int. We probably used, the legit one, right? No. Move RAX.
That's the
Printed. Oh,
oh, is this because we were going with the registers the last time?
well, I wonder if, so maybe I need a long, no, I have to remember, is that, It's doing quite a big thing there. Oh, I need to call my function. That would help. That would help. There we go. Yeah, not some random value. I was not thinking.
Oh,
So that gives us what we thought. I'm not sure if I need the long or not. Oh, let's see. I don't think it, like, unless we're getting really big numbers, probably doesn't matter. It'll probably just read the right number.
yeah.
Okay, so now let's suppose we wanted to add or do some other math. Like, we don't have to just do add, so add 8. We'll do that.
But what really throws me off is like I'm used to seeing a function with a parameter in parentheses and stuff, and it just kind of doesn't exist within this sort of thing. Kind of, you gotta keep it, kind of in your memory.
Yep.
As you're moving it over.
So, and let's do this. We'll make this a little bit. So if we got A, B, C, D. One, two, three, four, five, 6. So let's add all of these up and multiply that by G and subtract H. Right, so like just to do something, so we got to get it right or it's not going to make any sense. Okay. So push, move, move ESP, EBP, pop, return. All right, so I can pick some register that I want to use. It doesn't really matter. So let's just say we already know we got one argument in RDI, so we'll just sort of accumulate things in there. So we can say add RDI, RSI, add RDI, RDX. I'm mixing case here. I'm gonna make all the SQL people mad. I do my SQL. I don't do it uppercase just to make people mad, but because it actually doesn't matter in SQL. But okay. So this should be A plus B plus. Okay. So that should all be in RDI. And then I'm going to go grab a browser here.
And I guess my question is how does it know where to look in RDI instead of it basically using the same number to? Oh, never mind. Is it just adding? You just recursive. Never mind. I thought
I
that
can
was
explain it. That can be confusing, right? So add RDI, RSI. We'll add both of those together and then store the result here. So
yeah,
RDI is equal to RDI. I should have explained that.
Yeah.
So that's what that add instruction means. It's sort of implicit, right? Like it's got two arguments, but like two things are happening. It's adding them and then it's storing them in the one on the left side.
Yeah.
Okay.
Well, that and I thought they also all said move, and I was like, why is he moving the same thing? Like everything into the same register, but
yeah. So one that I always would throw my students off is the way that multiply works. So when you do a multiply, so I'm going to do IMUL. It doesn't really matter. So IMUL is signed, right? You have signed versus unsigned. So we'll just assume that we have a sign here. So we want to do sign multiplication. So first of all, I need to get G somewhere. So G should be at RBP plus 10. So I can pick any register I want. So let's say I take, see, one I've used, move RDX. And then I need to get the value of this. So that's RBP plus 10, if we did our math right. Okay. And so, right, because RBP is, the value in RBP is a pointer, right? So it points to the stack. The value in it is not what I care about. It's what it points to. So just like in C, right, this is a dereference saying, give me the value at that location, not just the value in that register plus 10, right? So I take the address of RBP, I add 10 to it in hex, and then I get the value at that location. So this is a, RAM is memory. So this is a memory access, right? And, one thing I did mention, right? You can't do something like move RDX, RBX, right? So I can't go get the thing at RBX and store it in the thing pointed to by RDX, right? I have to do that in sort of 3 operations. So I always have to move it into a register, and then I can move from a register back to a memory location, right? So this is bad. Okay. So I'm going to grab that argument 7, which is what, right, we said this was, right? So this is 1, 2, 3, 4 to 7. So I'm going to move, actually, I don't want RDX. Let me do RCX. I just want this to be clear. So if we look at how multiplication works, and don't worry, looks confusing. It's fine. I'll just sort of explain it. So the opcode.
Just a little bit better.
Yep. Hopefully it looks okay.
Yeah, that's better.
So, the way this is sort of worded is you're doing imul, and it's either 8-bit, 16-bit, 32-bit, 64-bit, right? So if we're multiplying, right, we're going to take, so we're going to take RAX, and we're going to multiply it by the other thing. So I'm going to need to use one of them in RAX. But what it stores it in, right? So if you take two 64-bit values and you multiply them together, you get a 128-bit value. And so the way that they handled that is they put the low 64 bits in RAX and the high 64 bits in RDX, right? So the gist of it is, if you had something important in RDX and you do a multiply, it will get clobbered, right? Whatever the multiply, so if the multiply at the top is 0, RDX will have 0 inside of it. So and it's the same for all of these, right? So it's, the 8-bit, okay, it puts it in AX because it actually has enough bits to do it. But all the rest, right, you're using these sort of 2 groups of registers in order to do that multiplication.
You've got to move, if I'm understanding it correctly, you've got to move whatever's in RDX out of the way before you add
if you care what was in it.
If you care what's in, yeah. If you care,
if you don't care.
If you want to use it for later,
yeah.
You got to move it out of the way, because both those values are going to take up our RDX and RAX, and then when you're done, you can move it back.
Yeah. All right, so I guess we'll pick RAX because I think I can use different registers, but we'll use RX. So I'm going to imul RAX and RDI, right? So RDI had my result from all of my adding. So I'm going to go ahead and multiply those together, right? And that should give me the result. I actually want to try and run this first, and then we will look at it. So let's do a So I'm going to put a couple of dumps in here to hopefully so we can look at it. And then up here, so move RDI 1, move RSI. So I'm going to pick prime numbers, hopefully if I can remember all of them. 2, just because that way, like, we won't get any coincidence of, so 5, 7, 11, yeah. I think that's the next one. So if I take all of those, 1 plus 2 plus 3 plus 5 plus 7 plus 11. So I should get 29. And now I'm going to multiply it by, let's say, 13, right? So I need to move, say, R10, 13, and do a push of R10. So that is my, I'll have to do the other one. I'll do the other one when I get to it here. But this should be how my function call should work, right? So I got those arguments. arg7 is the last thing that I pushed onto the stack. So then I should be able to say call add 8 numbers. And then I did a push here. So I'll do an add. I could do a pop. RSP, and it should be 10 hex. Yep. Yeah, 8 bytes. Okay. I could just have easily said pop R10, right? Pop the value back into the register that I had, but right, these are basically the same. Like, at the end of the day, they're the same type of thing. Here, let's make sure we got, I think I did everything. Okay. Just want to make sure. I didn't have to push anything, so dump registers should do the thing that I want it to do. What did I do? Oh, do I need to say? Oh, probably need to do that. All right, line 70. See, even I mess up, so 70. Oh. Oh. I'm using the wrong one. This is what happens when you do both. All right, moment of truth. Crash. Perfect. Perfect. Okay, so yeah, let's this is the learning moment. I'll break in this one, add 8 numbers, run. Okay, so we got to at least our function. That was good. Okay, so let's just I'll do next instruction because I don't want to jump into dump registers. I think dump registers should be right, but we'll see. So, and I'll make this bigger. Oh, not quite big enough. Okay. So RDI has 1D. So if we take 1D and base 10, that's 29. Hey, our number's right. Good job, us. Okay. So next instruction. Okay, so REX has 0D, which is A is 10, B is 11, C is 12, D is 13. So that's right. So maybe it's my dump registers. Did that crash? I think it did. It crashed in printf. Well, what did I do wrong? I did something. Well, I will, it's actually not important. So let's take this out for the moment. We can actually break. One thing that I do like to do is I just make a label randomly where I want to stop. So if I do a make and then I debug and I say break here, hey, I got a breakpoint. I can do run and I am at the location I wanted to sort of look at. So let's look. So RIX is D, RDI is 1D, which I think we did is 29. So, and then RAX is D, RGX is 3. If I do step instruction, RAX is 179, RDX is 3, which actually, that's interesting. Because it was 3 before. They might have changed the behavior of that. Like maybe if it doesn't need it. Let's see. That's interesting. I know in 16-bit that's what it did. Maybe it didn't. It shouldn't be that big, right? We're multiplying to like 179 in hex. 179. That's 377 divided by 29 is 13. Yeah. So it did our math right. That's interesting. I looked at RDX. Yeah, it says it's 3.
I guess I'm not following what the.
Well, it should be that multiplication should be small enough that the top would be 0. So if I was doing,
you wouldn't need that on register, is what you're saying?
Yeah, like it would set it to 0 because if you took the 128 bits, the top bit should be 0, and that should be. So I mean, this document here says, you know, what I assumed was true. But that is interesting. I'll have to look at that later. I mean, but it's doing the thing that we wanted to do. And then I was going to look at idiv, because that's the next piece that we're going to do. So we got that bit. I'm not sure why my one function's broke. We'll figure it out. I'll go and debug it after we're done. Okay, so we did our multiply, and then we were going to, well, let me do divide because I think that's more interesting. Divided by h. So we got to grab our value for h. So let's suppose we want to use, let's say RBX. So we can move into RBX. And what So if I wanted to get that next argument, what do you think? This is a quiz. And it doesn't matter if you fail, your best effort. What do you think we would use to get the value of h?
To get the value of h. Um, RBP. No, wait. Get the value of h.
Yep.
One,
So this should be
one,
A,
two,
B, C, D, E, F, G.
Be 6 registers, 7 registers.
So
I could do the RBP minus whatever that address would be, right?
well, so R7 is at RBP plus 10, right? So it's going to be the next one up,
So that'd be plus 4 more,
plus 8 more,
8 more,
right? So it should be at
18.
RBP plus 0x18, right? So it's eight more bytes, right? And if we had, so this is arg8, and then the ninth one would be, I mean, so if we write it in base 10, right? So this is at 16, base 10. This would be 16 plus 8 is 24. And then
Another way would be 32.
Yep. So each one is 8. In hex, it's, 8 plus 8 is 10 in hexadecimal. We'll probably, I'd like to probably go over that next time. Just like helping to learn like how base 16 works. That would probably be helpful in, doing some of these calculations. All right, so I moved into RBX the value from, so this is H, this one is G, just so we know where they are. And then, so similar to multiplication, and this is for integers, right? So there's like a whole separate thing for doing floating point or numbers with decimals. So there's a whole floating, they call it an ALU, arithmetic logic unit, or APU or something like that. But when we do division, right, so implicitly what it does is it does the sort of whole part and the remainder, right? So, when you did long division in school, you get both of those pieces when you do a divide. And that's why, like, if you look at a language like C, when you do integer division, right, it gives you the whole part that goes into it. And when you do mod or percent, it gives you the remainder, because implicitly the processor sort of does both of those at the same time, and just you get one of them when you're in C. You don't get both, which is actually kind of weird, but that's how C works, so, which is fine. So, and as it states here, right, so we're going to do 64-bit. So the quotient, right, is in RAX, and the remainder is in RDX for that division. So we should be able to do a divide. So I think I can do idiv. So if you do the division,
Okay, I was about to say, don't we need to move
well,
RBX first?
so I think there's two. I think I showed you actually. I think there's two versions there's a different versions of these. Ooh, that's super tiny. So idiv looks like that. I'm wondering if imul is the only one that has the. So I think there's an instruction that, like, imul, it will take 2 arguments, or you can do one where it implicitly uses EAX. So I think idiv rbx assumes that rdx colon rax divided by rbx. So, and this is where like a lot of students would, I think, get into trouble, right? Is it's actually using rdx. So I'm going to assume that this thing up here didn't quite do what I wanted. So I'm actually going to do move rdx 0, because I want to do, if you do a big enough division, you'll get a overflow, which will cause it to not run that command. So a lot of times they would not realize that it was doing this sort of, I'm going to assume all 128 bits are here, and when I do the divide, if it's too big, it won't fit, and then you get an exception on the processor, and then your program will crash, right? Because it tried to do that. So this is, from what I recall, what I typically would do. Now, that RDX had a value in it, so that was actually kind of interesting. So let's do our calculation and make sure that we get, what was the number we had? Let's see, we had 29 times 13. So 377. So let's divide that by 17. That should give us a good number. 22, 17 times, oh gosh. We'll see what the result is. Well, it'll probably be right. We'll fly by the seat of our pants. All right. So we're about on time. Okay. I'll put a thing here. Hopefully we'll get this done, and then you got a hard out, or you okay? Okay.
Not dead. No, I'm good.
All right. Well, 69. Invalid MIB expression. Oh, I put a comma. My bad. There we go. Oh, I know what I forgot. We got to add our other parameter. Okay. So here we did our 13, but move our 10. I said 17, push our 10, right? So we have to push them in the reverse order that we want to do them. So I need to, if I'm doing pushes, I need to push 17 first, and then I can push 13. So 13 is the closest, right? So it's on the bottom of the stalactite, and then 17 is a little bit older on there. And I didn't hit save. Okay. So I'm actually going to, well, actually, let's see. I might make this, is that readable? I want to be able to see, okay. I want to try and at least be able to see the whole thing. Okay, so next instruction. So we're going to move into RBX. So RBX has 0. We'll get the thing on top of the stack. So RBX has 11. Okay, that's great. We're going to move into EDX. Oh, I picked EDX. I wanted RDX. Let's do that again. Oh, come on. I get my R's and my E's mixed up. Oh, actually, huh. It didn't like me. Actually, it did, I did do it right. I guess it decided it didn't need to do the whole thing. Okay, let's do this again. Okay. All right, so RAX has 179. RDX we zeroed out. Go ahead and do a divide. So now we see that RDX has 3. So that should be the remainder. So we figured, okay, let's just make sure. Calculator. So we had 29 times 13. 377. Okay. Oh gosh. That's terrible. I don't know why you can't read that. All right, so then if I have 17 times, right, my remainder 16. That's not right. Oh, that's in hex. That's in hex. 16 hex is 22. So 22 times, we're dividing by 17. Okay, so times 17, 374. Okay, yeah, the difference, the remainder is 3, which is in RDX. So, looks like we did that right. All right, does all of that make sense other than the multiply, which is doing something slightly different than what I thought it was doing?
No, it's making sense.
Okay.
No problem.
Right, and then in our function, right, so we kind of talked about this earlier, right, so the implicit behavior of doing this function is, so we wanted the result, right, not the remainder of the division. So we should move, I mean, I guess it's there, move into RAX, right? Our result was in RAX, so that seems like it's fine. Now, the other thing that you typically want to do is, so 60. Is you want to save the registers that need to be saved. And I'm trying to remember which ones. So like when I did 32-bit, right, the only one you could clobber was REX. All the rest of them you had to sort of leave the same. Okay, preserved across function calls. So I need to save RBX if I use it. We do those already. And then R12 through 15, which I didn't touch any of those. So I need to save RBX. So in order to do that, I'd up here say push RBX. I think I did use it. Yeah. And then before I do my move, I need to do pop RBX. So because you want to sort of maintain this, right? Because if you don't, right? So like when on one of my earlier streams, I was looking at the 32-bit, so running 32-bit code and trying to do it um, such that it worked in 32-bit mode without like compiler errors, right? So there's a way you can do it where you position independent code and this just works. Um, so because of that, it was using EBX, so the EBX register to like save a value, and I wasn't saving that, and then it broke my code because I wasn't preserving that between calls. So understanding which registers you can clobber or get clobbered, right, is important. So if I had something important in RCX, right, and of course if I call the function and it has, you know, enough arguments, it's going to be clobbered, but like you need to be able to like save it, right, if you had something important on there, if you were going to use it.
Would it be just good habit to push stuff onto the stack, whether or not you think you're going to clobber it or not?
Yeah, I mean, so it is, right? You incur, right, a performance penalty by doing that, right? So
Uh,
if you're saving things that you don't need to, right? Those are just extra operations that, you know, if you're using it, yeah, save it, right? Like if I was using RCX, right, in here, well, I already clobbered it by moving the number 5 into it. Like I would want to push that. Like if I was using it, I would say push RCX. And then when I'm done, I'd say, well, you do the add and then you pop RCX, right? So I need to save it somewhere in order to make sure it doesn't get clobbered. So yeah, that's kind of the gist of how that does work. So
well, that
hopefully
makes
this is
sense.
helpful.
Oh yeah, yeah. Especially before the before stream discussion we had and this, like, makes way more sense. So
Yeah. Yeah, so I think you know, next time we'll we'll look at like hex numbers and like how we print them and how we calculate them. So, you know, we can go and maybe use some binary math to well, let's see.
it's been a hot minute since I had to do that. So it probably wouldn't.
Yeah, I'm trying to think of. I mean, we can not do the binary math yet. We'll do that maybe later because I think we'll probably want to do some learn how to do like if statements first. So you have to learn to compare, and we also probably want to talk about, you know, using variables. Like we put stuff in the data section, but we didn't like read and write to it, and
Mhm.
so I think we'll want to do that as well, so that we can say save something and then use it somewhere else. And you know, we also need to look at, right, we didn't have any local variables, right? So we could have used a local variable, and so we can do that as well when we get there. So don't worry, I got plenty of stuff for you.
Keep me busy for a while.
Oh yeah, I mean, you know, I usually taught. I mean, I taught it, and I would do like for my students, I'd have 2 videos a week that they had to watch. I'd have a lab, and then we'd have a day where they could come in and ask questions. And there was actually on Steam, there's like 2 games that are kind of related to assembly, and that like it makes you think like you're doing assembly. Like I can,
What are they called?
well, let's look. So there's 2 of them: human resource machine. And that's on like iPad, I think. And then I can send you links to Shenzhen IO. it's half off. So human resource machine is like, you got people and they're doing stuff and you kind of give them instructions, like, turn left or turn right or stuff. Like, you get to pick the instructions and what order they're in. Shenzhen is like you have a little computer and you write sort of an assembly language, right? So if you look at it might be really hard to see, but it's got like MOV P0 ACC, like that might sound to you like assembly, right? And you're like programming this computer and it's got like signs and switches and they're fun, but they also sort of blend, like this Shenzhen IO, it sort of blends in like the hardware side and the software side, because when you look at a computer engineer, they're sort of looking at that interface between like assembly and the actual hardware of like sending out a signal on a line or doing something like that. So Shenzhen kind of blurs that line in, and even if you do like a Raspberry Pi, right, you can get sort of that blurred level of like hardware and software, and we can get into that eventually. So then it becomes a business expense, right? If you're using it for work.
We can run with that. Yeah, I like that idea.
Yeah. So I'll put some. I'll send you these links here and
But kids, consult your your tax professional before doing all that.
Oh yeah, the obligatory.
Yeah, good.
I was listening to Planet Money and they were talking about the most overused tax advice on TikTok is personal expenses as business expenses. Which is true, right? Like, I mean, I buy a lot of computers related to business stuff, right? So, and in theory, right, you can do personal stuff on your computer. So yeah. But anyway,
Cool. Yeah, I'll check out both of these games, and then yeah, next week and the week after I'll be on the road. So do you want me? You just gonna just do those streams and I'll catch up afterwards, or?
well, what I'll do is I will. So some of the stuff I've been like, I'll probably go and I'll do some more streams, but I won't cover the stuff we're gonna talk about unless you're on stream, if that's all right.
Perfect, man.
Yeah, and then I have another friend who we'll probably do some additional streams, so probably there's going to be more stuff. I'm just going to put stuff on the channel and see what people like. But I'll do, so I made a separate channel for like concise videos of like, okay, this is how you do a thing, where I'll have everything, like I'll have a made example off screen, right? And I'll do it, type it up as I'm doing it and kind of explain what I'm doing. So those, will be coming out, as we go. So like, I'll probably do one over the stack and using that. I'll probably be doing a couple different variants, like, because like if you just talk about function parameters, right? You got 32-bit, you got 64-bit on Intel, and then you got ARM, right? And so those are all going to be slightly different. So I'll have probably 3 videos. So I might have to have 3 different sort of buckets of where things go. So I'll have stuff in there, and you can feel free to sort of do that. But all the stuff we're working on, right? We'll go through and I'll do it with you until you get to the point where you're like, you don't want to do that. I'm not gonna make you do it, but I feel if it's helpful to do it together, right? We should do that to help you out. So.
Yeah. No, that's perfect. That'll work.
Yeah, and I'll do the other streams, and I try and at least talk on them because people seem to like talking. So you can hear me mess up and
call a mistake out. Oh no, that's definitely wrong.
Yeah. Well, yeah, I was like, well, this is not working. Like just like we saw today, right? This isn't working. I'm gonna go figure out why, and it might take.
Sometimes that's almost a better learning experience.
Well, that's why I like recording them, but like, you know, they're more you know, people have to want to watch them, and I think it is useful, but you know, it's learning. It's learning for me. It's learning for everybody on. So
Yeah.
anyway,
Cool.
all right. Well, hey,
All right.
I appreciate it.
Yeah, no, same here. I really appreciate you taking the time, and like I said, I'll keep studying, and we'll do the hex and the conversion.
Yep, we got stuff to do. So
Yeah. All right. Peace
all
out.
right.